Yep. Okay. So I've got a recording starting now. I'm just going to. Yep. I think not going to have a trend. Oh, I got muted. Okay. Anyway, so I'll go back to sharing my screen and then we can move on to the next question. I'm sorry about the disruption there, guys. Just wanted to make sure that everyone could see it who needed to watch it later. Can everyone see my OneNote again? Sorry, I'm just replying to the original chat just to make sure everyone. Okay. Awesome. So now I think we'll just get moving. If anyone has any questions, we can sort through that. So next, now we get to the part where we're looking at capacitors and inductors. So the first part we're looking at is we've got to find the voltage, current, and energy stored in the capacitor under DC conditions. So first thing worth noting then is what happens under DC conditions to the inductor and the capacitor. So what does a capacitor look like in a steady state? Yes, so a capacitor is open. Alternatively, what is an inductor in DC conditions? Yes, so it's a short circuit. And we can use those two things to simplify this circuit greatly because we see that we can short out this inductor and that one, and we can open this. So that's a short, and that's an open. This allows us to get a circuit that looks something like this. Just to make it easier to read, I have actually moved the open 10 farad capacitor just to the top, just so it doesn't actually get in the way. And we see that this short down the side actually removes this 10 ohm resistor, but leaving the last 15 ohm, like so. So that is actually all that we're left with after simplifying this circuit. What this means is we can actually just find the current in the whole loop. Similar to before, it's just 25 on 25. Or I should just I'll just write it out. So it's 1 amp of current. We know now that we can find the voltage that they are after, which is just the voltage across the 10 ohm resistor, which is just done by using a voltage divider. So we can say that it's 25 times 10 over 10 plus 15, which just gives us, well, 10 volts. Now, the last thing to notice is that for energy, we get E half CV squared. So this is a unique equation for capacitor. The inductor has a similar one, and we can just use that. So we can go half times 10 times 10 squared, giving us 500 joules. So that one's a fairly quick little question, but only if you're aware that opening and shorting these inductors and capacitors can make a big change to your circuit. So, yeah. this one here. So that is a voltage divider where it says that V is equal to sort of the total voltage across, like the voltage drop across the whole set of series resistances multiplied by R. Say we're doing V1, it's R1 over REQ. So for us, the total voltage across everything here is 25 volts. The resistance we're after is 10 ohm, and the equivalent resistance is the addition of both the 10 and 15. Yeah, so it's the voltage across the capacitor, but as you can see, they're both in parallel there. And as such, they're going to be equal voltages. No worries. Okay, and now the next question is a bit of a this type of question, Quad 1 has tended to employ in the past few years because they can be a little tricky just because, as you'll see here, there are a lot of words. So this is where we take it. I'll just check if there's any questions. Doesn't look like it. Cool. So this is where we can take a second to try and just figure out what this question's asking. So it says the circuit below is used to take signals from a hi-fi system and amplify them so they can drive a subwoofer. Now, in terms of answering this question, straight away, we don't need it. That sentence doesn't matter to us. So that's the first thing we want to know. When we're breaking this down, next we look at that second sentence. When first turned on, the amplifier fails and applies 15 volts directly to the output. So at T0, we say that VA equals 15 volts. That's all we need from that second sentence. Then we can say when T equals 30 milliseconds, which is this part here, then we can say we say that the switch is grounded. So what we want to find is so that's our second. And then lastly, it's saying just all we want to do is find VC for T equals 0 to 60 M. Now for this, what we need to do is firstly, we need to remember the equations for capacitors. So does anyone remember the standard equation we used for the charging and discharging of a capacitor? It's a bit of a long one, but I think someone might be typing it out. But essentially, what we get is VT is equal to V infinite plus V0 minus V infinite, or not 8. And that's multiplied by, okay, I'm just going to move it slightly down so I can actually fit it all in. E to the minus T on tau. Okay, so what we need to do now is, firstly, we have to identify V infinite and V naught. So could anyone tell me what they think V naught and V infinite are? So what we can say is that initially, so at t equals negative infinity, we know the circuit is turned off. What that means is the switch is down, and because the switch is down, the circuit is grounded. We know that V0 minus is equal to V0 plus, and as such, we can say that V0 equals 0 volts. Then we need to look at V infinite. As they say, they're charging it to plus 15 volts due to the fault, and that means that V infinite is equal to 15 volts. So does that make sense so far? Now the next part is we need to find tau. So we know that tau is equal to RC, which is our time constant. So we need to go back up to the circuit and we see in this path here for the subwoofer, we have R equals 4, C equals 1,000 microfarads. As such, we can just say that tau is equal to 4 times 1,000 micro, which for us gives us 4 milliseconds. From there, that allows us to say that Vt for that first 30 milliseconds is 15 plus 0 minus 15 e to the minus t on 4m. From that, you can just simplify that, e to the minus t over 4m. Now we want to find t at 30m, correct? Because that is, if we go up, that is our second condition of after 30 milliseconds. Because of that, we will just do V30m equals 15 minus 15 e to the minus 30m on 4m. From that, what we can see is that we get actually very close to 15 volts. So we'll assume it's 15. This shows that it's a fairly fast circuit because it takes 4 milliseconds for one time constant. And does anyone remember how many time constants it takes if we have a circuit? So Vt, how many time constants does it take to charge up to our 15 volts? Or in general, how many time constants does it take? 5. So we can say this is 5 tau. And we can see that here. So 5 tau is equal to 15 milliseconds, which is less than 30. Because of that, we expect this result that at 30 milliseconds, we're essentially at 15 volts. Now, for when t is between 30m and 60m, we now need a new response because now it's actually been grounded. We see that Vt is V infinite minus V0 minus, or am I on something? I think I am. Give me a sec, I think I've, yeah, okay, that's a plus. Cool. So anyway, now we get our same equation again. We know tau is the same. So because we still have our same resistance and our same capacitance, tau is the same as above. We know that V0 is going to be 15 volts because it's as calculated. And now we have the system grounded. So V infinite is 0 volts, giving us the equation 15 e to the minus t on 4m. Sorry, I did some maths wrong here. That's meant to be 20. Awesome. Now, if we just, same as before, sub in 60m, oh, does it even after that? I think it is, so I'm just going to put that in as well. But same as above, we actually see that's roughly equal to 0 volts as well. So these two equations are the main things we were after in this. And our response, just so you guys have a bit of a grasp of what we're actually looking at there, is that it looks like this for the first part, and then that for the second, that being 15 volts. So we can see that is charging, and this is discharging. Okay. Did anyone have any questions about, should it be a negative? You're exactly correct. Okay, so yes, I see what you're getting at, and you're exactly right. So because we're shifting along by our 30m, we have to put that in there. Cool. Good spotting. And so, did anyone have any more questions about that? Otherwise, I will move on to our op-amp question. So op-amps are definitely something that you'll probably see one, maybe two questions on in the final, which they can be a little tricky, but should be able to do it. So we'll probably spend a little bit of time now just going through some of the op-amp theory. So in our basic op-amp, do anyone remember the features of, say, the voltages here that we can consider, as well as the currents going in? Yes. So in this course, we always have negative feedback. And what negative feedback means is that V1 is equal to V2. Additionally, an op-amp is known as a device that has what is called a high input impedance. What that means is that you can assume that I1 is equal to I2, which is equal to 0. So these are two very, very helpful assumptions that we can make to allow us to try and, do some calculations on these circuits. There are a range of different configurations we can use, but for us, we only look at a couple. I'll just give their what they look like. I won't give their names just yet or their equations, because we potentially might have to use them above, and that would be a bit of a spoiler. So I'm just busy butchering circuit. So here we see if I put a voltage source here, that is our classic non-inverting amplifier. And we call it non-inverting because the input is on the non-inverting input, and it actually ends up having a positive output voltage. Now, similarly, let's just have a quick look at our inverting amplifier, which is very much the same. However, we see now our input is on the non-inverting side. These are generally the two main circuits for op-amps that we look at in the course. However, there are a range of others, so I definitely recommend having a look at those. Examples: differentiators, comparators, integrators. There's some differential input stuff as well. So it's worth having a look at those because they could throw any at you in a final, particularly when it's open book. Now, what we're going to do is, for this question, first, let's identify what topology of an op-amp we have. So could anyone answer to me as to what they think these op-amps are? Are they inverting, non-inverting? Are they something else? And then we can go forward with the calculation. Correct. So what I'm just drawing out is actually the path to... Awesome, both of you are bang on. So what I'm just drawing out is the path to the source for both op-amps. We can see the positive terminal is entered by the top, and by the bottom op-amp we have the negative terminal. Hence, it is an inverting amplifier. For us, this allows us to calculate the gain, and the gain is essentially our most important factor for these op-amps. So for a non-inverting, what we get is that AV, which is our gain, is 1 plus, and what symbols are they using? So they say RF, which is our feedback, on R1 or RI. We know that V out equals AV times V in. So we get 1 plus RF on R1, V in. So we just need to change some symbols around. So we go 1 plus, let's just check. So we have here, that is RF. It's R1. So we get 20K and 10K. And V in was VS. So V out equals 3 VS. So that is how we do our non-inverting. For our inverting, it's slightly different. Now we put negative out the front, and we no longer have the one term. So similarly, V out is the negative RF over R1, V in. However, now RF is 30, R1 is 10K. So we get minus 30K on 10K V in, and V out equals minus 3 VS. So interestingly, we see that both of our voltages are equal, but negative in magnitude. This will come back to be a little bit interesting when we get... So I actually did, just worth noting, I did just knock out 2 parts. And lastly, we just have to look at what is our voltage V0. So the way to view what the voltage across this speaker is to actually just take the difference in this voltage V1 and the voltage V2. And what we see, we know that V1 is equal to 3Vs, V2 is equal to negative 3Vs. Can anyone see, just sort of by eye, what they reckon this will turn out to be? Because there is another way to do it, which is the way I'll formally do it. But because we have the top is positive, the bottom is negative, we can sort of see that there's going to be about 6 times Vs across. And we can actually verify that by using KVL. So now the loop we're looking at is because we have, interestingly, we have a ground path. So if I remove these, we see that we have a path like so. And because these two are grounds, they're actually, you can actually sort of view those as connected. Because of that, what we see is we get negative V1 plus V0 plus V2 equals 0. V0 equals V1 minus V2. And this actually matches what we were just looking at before, that we get 6 Vs. And they just want to see that Vs on V0 is 6. And this actually raises a very interesting comment about things that we can do in using op amps, which is we can make a much larger load be driven just by using some circuitry in between. Because this output voltage at the speaker is 6 times the size of what we've input, which is very handy to use. Also, this is backwards. That should be V0 on Vs. Did anyone have any questions about that? Because if not, I will head into the next op-amp question, which gets a little interesting because as we see, we now have 2 things that kind of make this circuit look a little bit frustrating. Oh, yeah, I can draw out that mesh as a closed loop. So if we look up here, it's a little tricky to draw, but the idea is that because this ground connection we're looking at, if we remember our original nodal analysis question that we did at the beginning, we had something like so, where everything was connected. So what we could say is that it would look something like this if we were to draw it out in the circuit. So in fact, this is actually a worthwhile way to think about it, because this is exactly how they're implemented in real life, is that we would have had something like this. So V0 so that would be V1 and that would be V2. This would be V0. So then we get our mesh looking like this, because these grounds are actually going to be connected together and grounded like so. So then we can just say that our mesh looks like that. Does that make sense in terms of what the closed loop would actually look like? Naturally, I haven't drawn out all the circuitry because that would be quite a complex diagram, but this is how it's actually what it actually looks like, and that is a common way it's represented. Okay, now we get to some AC circuit analysis. This one here, all the impedances are already supplied. So what that means is, so as impedances are supplied, so we just get to treat this like a normal circuit. However, we don't always have that. This is where we need to consider the idea that we have, sorry, I'm just going to check if there's one later on that this explanation works a bit better on. Yes. So for now, let's go with the idea that we can treat this just like a normal circuit. Could someone tell me what they think this topology is for the op-amp? Because that'll be our first step, just like before. So what makes you think it's a voltage follower? Because there's actually a little bit of a nasty trick here that makes it seem a bit more tricky than it actually is. Unless them just doing something really annoying. So this might just be a quirk of the circuit diagram. So are you saying that we've got, like so, we've got a, yes. Okay, so this is where it gets a little curious. This is left very ambiguous as to whether there's a connection here. Let's assume there is, because if so, then you're exactly correct. My first thought was that this actual feedback resistor was included in a loop like this, but I now realize that that was very incorrect an assumption. So good job on pointing that out. So now let us have a look at trying to solve this equation. Firstly, we want to use our identity that we know that V plus is equal to V minus. We see that V minus is actually connected to the output. Hence, that means that V plus is also equal to V0. That is very helpful for us. It makes looking at these nodes a lot easier. The only additional node we actually need to add, we'll just call V1. So by looking at nodal analysis, we'll look at that current there. Let's just put in some polarities. Although I will note that in AC circuits, naturally polarity is a little bit of a thing that we don't really like. That's not how we see it in the circuit. I'm just adding those to assist with the polarities for the nodes we're going to look at. So let's do KCL at node V1. So we see that we get 6 angle 30 minus V1. And that is going to be over minus J4K. That is the only current entering. The other two are leaving, as we can see by the positive terminals both going that way. This allows us to say that V1 minus V out over 10K plus V1 minus V out on 20K. So this is actually our first nodal equation, which we can do some rearranging to try and find something that looks a little nicer. So Do people want to see me do this rearrangement because it's got some complex numbers in it, or do we want me to skip just to the final result? Because I'm happy with either. Skip? Okay. Anyone really passionate about not skipping? Otherwise, I'll just give you a final answer. Is that a no, you don't want it skipped, or? Because what I can do is just, so I'll do some lines, I think, just so we get the gist of it. Okay, so that is actually not going to be that, that's going to be 20 equals minus J8. So that's just me multiplying everything through. From there, we can actually, so what they do in the solution, I believe now, is they divide the 20 back, which, yeah, doable. But I think it's, yeah, okay, I'll just do it that way just for consistency. Minus J. Okay. And then from here, if we multiply it out and rearrange, yeah, this is the last line I'm going to give, is just 6 root 30, 1 minus J 0.6 V1 plus J 0.6 V0. And this is the main equation we want to look at. So additionally then, now we want to do KCL at the next node. For us, this is actually going to be our V plus node. If we go up, we see that we have one current going in, one current going out, as we know that this current is 0. So we say that we get V1 minus V out over 10K is equal to V out over minus J2K. This is quite a sort of much simpler one. And that's just, sorry, I'm just having a moment. So V1 on 10K minus V0 on 10K is equal to V0 minus J2K. Okay. And from there, that could just be rearranged to give V1 equals 10 minus J2 over minus J2 V0. And we can actually use that factor. So I'll just quickly calculate that, which gives us 5.1 angle. I'm in radians, delightful. Okay. Anyway, so that is our second equation. And lastly, we just want to put, if we put 2 into 1, that's just a matter of just chucking in numbers and rearranging. And what we end up with is we get V0 is 6 root 30, or 6 angle 30, like so, which gives us 0.934 angle negative 21.38 degrees in volts, like so. So does anyone have any questions about this this one. Essentially, it's the exact same as the DC questions we've already seen. Because we're supplied the impedance values, the only extra challenge is that we have a calculator as required, like our complex calculator that we need. So, yeah. Do we have any questions for that? Otherwise, I will head on to the last section of this paper, and then hopefully, if we have time, I can see if you guys have any questions. Sorry guys, I just need to be 1 second because I just need to one of the requirements for these, which is just sending screenshot. Awesome. Sorry, just for archive to screenshot that. Okay, cool. So now we get back to another question that has a lot of words. Less than before, but still trying to make it more complex than we necessarily need to read. But before we completely deconstruct the circuit, let's look at AC signals. So does someone remember the generic equation we use for, oh yeah, so the final answer, let me just check. So V0 is just here. So it's 0.934 angle negative 21.38 for that one. No worries. And yeah, so does anyone remember the normal way we represent an AC signal in time domain? So say I just wanted to say VT equals awesome. So it's cosine omega t plus phi, like so. And obviously, this is not exactly what we want to work with the whole time. So we use what we call a phasor. So with the phasor, we have Vm angle phi. And this is usually represented by some bolded version of the original symbol. Very hard to do on paper, so I just kind of scribble it to make it more standing out, but it doesn't really matter. It's usually a difference between a capital and lowercase. However, this isn't everything because we also need to convert our impedances into a frequency domain. So we now have a formula for the impedance and so the impedances of capacitors and inductors. Do people remember what they are? Because that is our second key we need to consider. Awesome. So first we have our inductor, which is J omega L, and our capacitor is just the inverse of, 1 on J omega C. And so we can use both of these equations to simplify our circuits and turn it into something in frequency domain, which allows us to use it with our phasor. With that, let's head into the question. So firstly, we want to express the voltage at the amplifier output, VA, as a function of time and then as a phasor. So the first thing we need to look at is V in, which gives us some pieces of information there. So first we see that we have 500 millivolts RMS, and it's a frequency of 1 kilohertz. So, does anyone remember what RMS voltage means? So, basically, RMS voltage is the AC voltage divided by √2. So, it's also known as a root mean squared. And not that it really matters for us in this course, but it is worth noting that RMS voltage is divided by √2 only for sinusoids. And that is just an identity we know through, I believe it's an integration. So this is the first thing we need to look at. We see that VRMS is VAC over 2. Hence, VAC is √2 times VRMS, meaning that our output voltage is 0.5 times √2. I'm not going to simplify this just yet because we've got a couple more steps to go through. The next part is if we go to VA, we actually go through an amplifier with a gain of -20. So this will actually change our input even more, because that means our gain is -14, -20 times 0.5 times √2, which gives us -14.14. And that is our first key identity. Next, we need to find omega. So we know that omega, same as 2 pi f. In this case, f is 1,000. So let's just say this is 2,000 pi, because it's much easier to leave it in terms of pi for these situations, and its unit is radians per second. Hence, we can say that VAT is equal to -14.14 cosine 2,000 pi t. However, there is something I'm missing. Does anyone know why this is not a quote-unquote legal voltage we can have, particularly when we're trying to convert it to... Yes, correct, Nick. So VRMS is VM on √2 for a sinusoid. And so that was the first operation we had to undo when we were supplied with an RMS voltage. Okay, so exactly right. So this here, we can't have a negative magnitude. And because of that, we need to move that somehow into the cosine. Does anyone know how to do that? Because we want it to be some form of, so we've got 2,000 pi t plus phi. And now what would that phi be? (180), exactly right. Generally, we use -180 as a convention and this will be our voltage. Now, this can be converted into a phasor just by taking those two key values, saying VA is equal to 14.14 angle negative 180 degrees. And that is our first part of this question. Yeah. So now we have our voltage phasor. Now they want to find V out across the speaker. So let us just quickly have a look at what they've given us. So I'm just going to put a little ground here just so we know what we're looking at. Now, we have 1.5 millihenries of inductance there. As we mentioned before, we need to convert this to frequency domain. So, using JWL, we have J times 1,000 times 1.5 M. So, 1,000 times. So that just gives us J 1.5 ohms. What I'll do is I'll leave that, but I'll put above it. Okay, and now what we can see is actually that instead of doing anything fancy in terms of finding currents or that sort of thing, all we actually need to do now is just use a voltage divider. So I don't know if Inma still talks about voltage divider being her favorite equation in ELEC, but it is very handy and you'll use it a lot. It should be 2000 pi. You're spot on. Thank you for spotting that. Yep. And so that gives us J 9.42. And now we'll get to our voltage divider. So what we see is V out is VA times the resistance we're after, which is our 8 ohm, over the total resistance, which is 8 plus 1 plus J 9.42. From this, if we were to just take this and put it in a calculator, we would actually get our answer straight like that. And what we find is we get 8.68 angle 136.69 degrees as our voltage. So does this make sense for everyone? Okay, so what we'll do next is we've got to look at the average power consumed by the internal resistance, the 1 ohm resistor. For that, we use this equation that P equals half VM IM. As we're looking at resistances, we can once again convert it using our Ohm's law to give half V squared M over R. And now, or alternatively, half IM squared R. For us, it's very likely to see that we can probably calculate I easier because we know that I is just going to be V out over the 8 ohm resistor, which gives us that 8.68 angle 136.69 degrees over 8. I guess 1.085 with that same phase angle because there is no phase change on the bottom. Hence, we can see P average is 1.085 with this same angle squared multiplied by 1. And now I wrote that out. I realize that. So you only need the magnitude because that's all we're concerned with. And that gives you 0.589 watts. And that is our solution for finding the average power. And now for the last question or the last part of the paper, which is another average power question. However, this one, there's a little more to it because, as you'll see, much more complex circuit. Now, it looked at, even though I say it's more complex, it's still largely simple. So for this one, do we reckon mesh or nodal would be easier to do? That's probably our first place to look. So for me, I reckon our best plan is to do nodal, as we have only the two nodes we have to look at, rather than 3 meshes and a super mesh. So we'll look at those. I'll just quickly draw the directions of all the currents just so we can get some consistency. And now let's get cracking. So using nodal analysis. So at V1, we see we get 6 angle 0 is equal to V1 over J10 plus V1 minus V2 over minus J20. So this can actually be rearranged. So we get V1 equals 120J minus V2. And that will be the equation we are after. Now, if we do KCL at V2, if we look up, we see first we have 0.5 I naught entering, plus we have that V1 minus V2 over negative J20 entering, and leaving, we just have the 40 ohm resistor, like so. Now, before we go and simplify this, we just need to find a value for I naught. We see I naught is the current passing through the capacitor. As such, we can say that I naught is equal to V1 minus V2 over negative J20. So what we can do is we can actually pass that down here. So we get, I believe it's 1.5 I naught. Yep. 1.5 I naught is V2 on 40. That is very handy for us. But then if we just expand this out back, so we get our 1.5 V1 minus V2 on minus J20, V2 on 40, and then we rearrange that, we end up getting V1 equals 1 minus J on 3, V2. And then we can do, and then by equating the two, because we see that we have an equation relating to V1 here, and we have an equation relating to V1 above. So 120 minus V2 is equal to V2 1 minus J on 3. This allows us to now solve for V2, which, just interest of time, I'll just quickly sort of get that answer out. So that is V2. And as we're concerned with the average power across our 40 ohm resistor, we know that the voltage across the V40 ohm resistor is as such. And so the power is going to be half Vm squared on R using our equation from before. Gives us 43.68 watts. I went through that last question a little bit quickly. So did anyone have any questions about that one? Okay, if not, that brings to an end the sort of formal part where I've run through this midterm. No, not midterm, sorry, final. Did anyone have any questions for me or examples they wanted me to run through or explain how to do before we wrap up? Because we still have about just under 20 minutes left that I'm happy to use to go through anyone's concerns. Am I going to post workings? Yes, I'll post it in the chat later when I get some time today. T1 final exam. I don't have a copy of the 2020 exam. Oh, that's a lie. I did that exam. So did someone potentially actually have the that final exam question? Like, if you could send a screenshot through, I'm happy to explain how we do it. Okay. That's a very good question about the angular frequency. Yes. So in this situation, that's a good question. As frequency is not specified, you can assume that the angular frequency is actually equal. If they give you two separate frequencies, though, do you know what you have to do for that calculation? Because that's something that wasn't actually in this midterm. Okay, so that is actually when superposition comes in very handy. So basically, when you have different frequency voltage or current sources, you can just use, you can essentially just use superposition to find both separately, which does mean calculating two sets of impedances as well. It's possible they'll ask a question on that, but it also takes a bit of working, so I wouldn't be surprised if they don't. Okay. So I'm going to look at this. So is it Q4A? That's a very good question about the power. I'm honestly not 100% sure about with power whether you can use superposition, because you are correct, not linear. But Yeah, so if you're trying to find voltages and currents, you can use superposition. Yeah, but that's a very good question about the whether you can use superposition for power. I'm usually in the camp you normally can use superposition for everything, but that's very likely not true. I would definitely recommend asking Inma about that. Honestly, sorry I couldn't give a stronger answer. Okay, so for this question, what we want to calculate is well, really all we want to do is find V naught. What this means is that we just need to try and find V naught, as it says, as a function of VI. To do this, there's a couple ways we can go about it. We could potentially use some nodal analysis here and here. We could also, if we wanted, we could just do mesh analysis as well. My view would potentially be that it would be easier to do nodal analysis because we can just treat VI as a source. Source transformation, yeah, that would definitely be possible as well, because what you'd be able to do is if we replace this with a source like so, we can turn this voltage, we can turn the voltage and resistance into parallel. Sorry, I'm just going to draw that very quickly, like so. Is it like that? Yeah. Then obviously you can combine those two. Then you turn it into, sorry, this is going to be a voltage, and I'm just going to call that an impedance now, like so, and a resistance in series with a capacitance. And then you can just use voltage divider, actually. So this one will always stay as VI, however, this resistance will keep changing. So that's a Z. That's that original 10 ohm. That's that J10. So naturally, so VI we aren't given. So what that does mean, and the one bit that could make this quite complex, is that you're now chucking V1s around everywhere. For example, do you know what the resistance would be when we convert this to a current source? Okay, are you not sure about the conversion to current source? Let us. So what I'm just going to quickly do is go back to our midterm and look at source transformation. So what we see is we have transformation where you use V equals IR with I staying constant to try and find that change in I. So what we get now, if we head right down to the bottom, is, so we actually end up getting I is V on R, so we get VI over what was previously a 10 ohm resistor. Then we have a 10 and a negative J10. So then plus minus V naught, negative J10. So that's our first source transformation. Now, the second one, so this is 10 in parallel with minus J10 equals, so I'm just gonna, part of the working I'm just going to do very quickly, sort of just to, so that's 707 angle. Oh yeah, awesome. Okay, so here we have that, and V is going to be IR, so it's VI on 10 times 7.07 angle minus 45. And then lastly, we just have to use a voltage divider. So VO equals VI on 10 times 7.07 angle minus 45 degrees. And we have minus J10, which is what we're concerned with. And this would actually be our final answer. Naturally, you can simplify all that. Yeah, so what I did was I used source transformation twice because that gave us every element in series, which is way nicer to do. There are other ways to get to this circuit. However, none of them are available for us. So source transformation is the best way. Otherwise, I would be approaching this using nodal, because that's just my preference of how I like to think about things, but source transformation also works. Hey, did anyone else have any other questions they wanted me to look at? Okay, if not, I reckon I'll use now as an opportunity to start wrapping up. Thank you so much for everyone that joined me today. Thanks for putting up with some technical difficulties we had earlier. But yeah, thank you so much for coming. I'm just going to stop sharing now, and I'll also just turn on my camera. So yeah, thank you so much for everyone that could make it. I hope you guys took something out of it. We'll share the recording to our YouTube channel that has also got past recordings as well. So if you're curious about, say, what I did for the midterm or what we did for the final at the start of the year, that is available there. Additionally, I will post my working out onto the chat of actually both meetings. So the previous one where it didn't record and now this one, just so everyone can get that. Yeah, so thanks so much for coming, and yeah, good luck with your final exam.